You ever wonder how all these different computer systems, the ones built by different teams in different countries, can somehow agree on what something simple like a customer actually is? Well, today, we're diving into the digital Rosetta Stone that makes all of that possible, ontologies.
So here's how we're going to break it down. First, we'll see why our data is so often lost in translation. Then, we're going to literally take an ontology apart to see how it ticks, and we'll get really clear on why it's so much more than just a database. After that, we'll look at a real-world example that is, frankly, mind-blowing. And finally, we'll uncover the secret to making a really good one. You ready? Let's jump in.
Okay, Section 1, a Rosetta Stone for data. It's kind of wild when you think about it. We have all this incredible technology, but it all comes down to a really simple and honestly a very frustrating problem. How do you get two different computers to agree on what a single word means?
So just picture this, right? One system in a company calls someone a student. Another system calls that same person an advanced learner. Now, you and I, we know they're talking about the same thing. But to a computer, nope. Those are just two completely random, totally unrelated strings of text. It's like a digital Tower of Babel, and it stops data sharing dead in its tracks.
And that right there is the multi-billion-dollar question. How do you solve that problem? How do you get all of these different systems to finally speak the same language?
And that's where the ontology comes in. Now let's just push that jargon-heavy definition aside for a second. At its heart, an ontology is just a shared rulebook. It's a file that basically says, hey, you two systems, that thing you call student and that thing you call advanced learner, yeah, they're the exact same thing. It's the Rosetta Stone that finally lets machines understand each other.
So what does one of these digital rulebooks actually look like under the hood? Let's find out. In Section 2, we're going to deconstruct an ontology, and we'll do it by taking a simple English sentence and translating it all the way into code a computer can actually process. We're going to use this one simple fact from what's called the African wildlife ontology. Each lion eats only herbivore and eats some impala. It seems totally straightforward to us, right? But for a machine, this sentence is a minefield of potential confusion. Let's see how we fix that.
So here's the very first step toward clarity. We translate that sentence into a more structured, logical form. Notice how we're making the relationships super explicit. A lion is a subclass of things that eat only herbivores and eat some impalas. Just by doing that, all that ambiguity, it just starts to melt away.
This logic can also be turned into a visual, like a diagram, which is incredibly helpful for the domain experts who aren't coders. I mean, here you can just see it, plain as day. You've got the concept, or the class, which is lion. You've got the relationship, eats, and the rules that define that relationship. It only eats herbivores, and it does eat impalas. Simple. And here it is. This is where the real magic happens. The final machine-readable code. I know, it might look a little intimidating, but this is where all the power is. See how that simple phrase, eats only herbivore, got transformed into that razor-sharp instruction, all values from herbivore? That level of precision is what lets a machine reason about this knowledge with zero mistakes. Okay, so right about now, you might be thinking, hang on, this just sounds like a really, really complicated database. And you know what? That's a fair point. So in this next section, let's break down the crucial differences.
The key difference is really this. A database is for storing facts. An ontology is for defining rules. And that leads to this huge distinction in how they think. A database has a closed world assumption. If you ask it, if I have a sister, and there's no record of one, it will say false. But an ontology, it assumes an open world. Ask it the same question, and it will say, I don't know. That little difference is everything. It lets ontologies deal with incomplete information and even figure out new facts on their own.
All right, enough theory. Let's see how this stuff actually plays out in the real world with a truly massive example. Welcome to Section 4, Ontologies in the Wild. You're about to see just how big of an impact this technology can have. This is where it gets absolutely amazing. Get this. A database in Japan has an entry for a gene. A totally separate database in the USA has an entry for another gene. They're on different continents, different systems, using different names. But look at step 3. Both of them have been tagged with the exact same ID from that shared rulebook, the gene ontology. And bam, a connection is made. For the very first time, these two systems now know they are talking about the exact same biological process. And the scale of this is just, it's hard to wrap your head around. The gene ontology defines over 40,000 biological concepts. It's a shared language that connects thousands of scientists all over the globe, turning what used to be these isolated islands of data into one single, vast, interconnected continent of knowledge. It's incredible.
But, and this is a big but, not all ontologies are created equal. Their power is tied directly to how precise they are. So in our final section, let's look at what separates a good one from a not-so-good one. The goal, always, is high precision. You want the knowledge that you intend to capture, in this case African wildlife, to be a perfect one-to-one match for what your ontology can capture. The rules need to be a nice, tight, accurate fit for your world. But here's what happens when you have low precision. You still want to talk about African wildlife, but your rules are just too broad, too sloppy, and all of a sudden your ontology starts including things it absolutely shouldn't, like polar bears and penguins. That's basically a semantic bug, and it can cause your system to make some wildly inaccurate and just plain wrong conclusions.
So what's the bottom line here? Let's recap. Ontologies are those shared rulebooks that let computers agree on what things mean. They don't just define concepts, they define the crucial relationships between them. They create a common language to solve massive, messy data integration problems. And, as we saw with the gene ontology, they can power global networks of knowledge that are literally changing the world.
Ultimately, the real power of an ontology is its ability to create perfect clarity out of complete chaos. And that leaves us with a pretty fascinating question to think about. In our increasingly complex, data-driven world, what other knowledge is still out there just waiting for its Rosetta Stone?